Graph traversal refers to the process of visiting each node in a graph. The traversal is classified based on the order in which the nodes in a graph are visited. One of the main issues of graph traversal is that it is possible to visit the same nodes more than once if the graph contains cycles. There are many reasons why we would want to be able to traverse a graph. For example, we can find the shortest path between nodes, analyze networks, generate mazes, and compute maximum flow in a flow network, for example for water distribution. There are two common algorithms for graph traversal: depth-first search and breadth-first search. The depth-first algorithm starts at the root and explores as far as possible along each branch, reaching a node with no more edges, or reaching an already searched node and having to backtrack. The selection of the root node is in general arbitrary. However, for a tree, the root node is selected. To perform a depth-first search, use recursion to visit all nodes reachable from a node V. The algorithm goes in this order. First step, mark V as visited. Second step, for each edge leading from V to U, do the following. If U is not visited, set V to U and go back to step 1. Looking at this graph, using a depth-first algorithm, one possible order of nodes that you will visit will be A, B, D, E, C, F. Some of the applications of depth-first search include finding connected and strongly connected components, topological sorting, and solving puzzles with only one solution. Let me now show you another way to traverse graphs. A breadth-first search starts at the root node or an arbitrarily selected node in a graph, and it explores each unsearched neighbor of the selected node before moving to the next level of nodes. To perform a breadth-first search, you use a queue to track the nodes that need to be visited next. To start with, there is an empty queue, Q, and an arbitrary node, V. First step, mark V as visited and push it to Q. Second step, while Q is not empty, repeat the following. First, pop the first element of Q called F. Then, for each node U connected to F, if U is not visited, mark it as visited and push it to Q. Looking at the same graph, using a breadth-first algorithm, the order of nodes that you will visit will be A, B, C, D, E, F. Some of the applications of breadth-first search include finding the shortest path between nodes, testing bipartiteness of a graph, and computing the maximum flow in a flow network.